Today's talk is by XiaoLin Danny Shi on slice spectral sequences of height 4 Leuventate theories.
All right, thank you very much. I want to thank the organizers, Dan, Hannah, and JD for the invitation. And I still remember the first eCHT talk I went to. It was by Mackey. And when Dan first created it 3 years ago, Dan wanted this to be a place where people can come in and talk about computations. So that's what I'm going to do today. I'm going to talk about some computations. So here's a spectral sequence. And here's another spectral sequence that I want to talk about. Now, these two spectral sequences, you can see they look kind of similar. And in fact, they are. They're both the slice spectral sequence of two different spectrums. And the goal for today's talk is to explain what are these two spectral sequences. So to start, I want to start with the Tia's real K-theory, Kr. So I want C2 to be a cyclic group of order 2 with generator tau. Then by real space X, I just mean a space X equipped with a C2 action, which means there's a tau action on X. And if I act on X twice, then I get an identity map. Now, once I have a real space X, a real vector bundle, E over X, is equipped with the following data. So E itself will be a complex vector bundle over X. And E itself is a real space. And the projection map P from E to X has to be C2 equivariant. Now, furthermore, there's a tau action on X. So that induces a tau action on the fibers. So tau induces an action from E of the fibers over X to the fibers over tau X. And I want that map to be anti-complex linear. By that, I mean if V is a vector and Z is a complex number, then I want tau of Z times V to be Z bar times tau of V. Now, I just want to remark that this is not a C2 equivariant complex vector bundle, because for a C2 equivariant complex vector bundle, tau of Z times V would be Z times tau of V. But I want this tau map to be anti-complex linear. Now, if I take all these real vector bundles of E over X and I apply the Grothendieck deconstruction, what I get is the Atiyah's real K-theory, Kr of X. So that's what Kr of X is, coming from real vector bundles over a real space. Okay. So this theory is so Kr itself is a C2 equivariant spectrum. Okay. Now there's another C2 equivariant spectrum, and that's called MUR, and it has to do with complex cobordism. And MUR itself is called the real cobordism theory. So I want to quickly explain what is MUR as well. So if I have BUN, then I want gamma n to be the universal bundle over BUN. And I can take its Thom space, which I'll call BUN gamma n. Now, suppose I have the universal bundle over BUN plus 1, gamma n plus 1. Then when I pull that back to BUN, gamma n plus 1 splits as the sum of the universal bundle over BUN and the trivial bundle. So what that gives me is that it gives me a map of Thom spaces. It gives me a map from the twofold suspension of the Thom space over BUN to the Thom space over BUN plus 1. And I can piece all these maps together, and it gives me a Thom spectrum, which is the complex cobordism spectrum, MU. Okay. Now, it turns out everything I said could be done C2 equivariantly. So BUN is actually a real space where the C2 action is coming from the complex conjugation action. And gamma n becomes a real vector bundle. And I can do the similar construction as before, take its Thom space. But now the classical map from the twofold suspension of the Thom space over BUN to the Thom space of BUN plus 1 has a C2 equivariant lifting. And the 2 becomes a row suspension. So rho is the regular representation of C2. The underlying dimension is 2. And this is a C2 equivariant map of real spaces. And I can piece all these informations together, and that will give me a C2 equivariant spectrum called the real cobordism spectrum, MUR. Okay. Okay, so now we have two theories, Kr and MUR. They're both C2 equivariant spectra. And their underlying spectra are Ku and Mu, the complex K theory and the complex cobordism spectrum. Now, if I look at their C2 equivariant spectra, so I can take their C2 fixed points. the C2 fixed point of KR is KO, the real orthogonal K theory. The C2 fixed point of MUR is harder to describe, but it has been completely computed by Hu and Krish. Okay, so now if I look at pi star of MU, pi star of MU by Quillen's theorem is a Lazard ring, which classifies.
Can I ask a question?
Yeah, of course.
What about the geometric fixed points?
The geometric fixed point of KR is trivial, and the geometric fixed point of MUR is MO. Okay, so if I look at MU, pi star of MU, that is the Lazard ring, and that classifies formal group laws. So above pi star of MU, there's a universal formal group law. Now we have MUR, and there's the extra C2 action. So the C2 action induces a C2 action on pi star of MU, which is this, which I denote by this. And this carries a universal property as well. So in particular, it carries the universal C2 equivariant formal group law, where the C2 action corresponds to the -1 series. Okay, so there's a universal property that's carried by pi star of MU together with the C2 action. Now, if we localize at the prime 2, then classically MU splits as a wedge of suspensions of BP, the Brown-Peterson spectrum. And this is true C2 equivariantly as well. If we localize at the prime 2, then the MUR splits as a wedge of suspensions of BPR. Okay, so this is going to be a talk about equivariant homotopy theory. So I want to explain some extra features you get in equivariant homotopy theory. So I'm just going to do it by example. So suppose X is a C4 spectrum. Then what I can do is I can take the C4 fixed points of X. I can take pi n C4 of X, which is the C4 equivariant homotopy groups from Sn to X. So I take the C4 equivariant map from Sn to X, where Sn is equipped with the trivial C4 action, and I model that by homotopy. So that's one thing I can do. I can take the homotopy class of C4 equivariant maps. But what I can also do is that, well, X has a C4 action, but I can just restrict my attention to the C2 action, where C2 sits in C4 as a subgroup. And I can take the C2 equivariant map from Sn to X, and I model by homotopy. And also, I can just forget the C4 action and treat X as a non-equivariant spectrum and take its usual classical homotopy groups. Okay, so in this case, when X is a C4 equivariant spectrum, I have three kinds of homotopy groups. One is about the C4 equivariant, one is the C2 equivariant, and one is the non-equivariant. And there are maps called the restriction and transfer maps. That's coming from the maps between these stable G sets. So the restriction map always exists, and the transfer map only exists stably. But the point is, I have different homotopy groups, and there are maps between them. So I get extra data. And this extra data is what's called a Mackey functor. And all this data is denoted by pi n of X with an underline to denote that it's actually a Mackey functor. So in equivariant homotopy theory, Mackey functor is supposed to play the role of abelian groups. So what I mean by that is that they form a abelian category, and makes sense to talk about kernels and co-kernels of Mackey functors. So it makes sense to talk about exact sequence of Mackey functors. And I can do homological algebra with Mackey functors. And in a second, you'll see it makes sense to talk about the slight spectral sequence of Mackey functors. Okay, so that's one extra feature you get, the structure of a Mackey functor. There's another extra feature, is that, so non-equivariantly, by pi n of X, we mean the homotopy class of maps from Sn to X. Equivariantly, however, we have more spheres. So we have the representation spheres. So if V is a G representation, then I can take this one-point compactification to get a representation sphere SV. And if X is a G spectrum, I can define pi VG of X to be the G equivariant maps from SV to X, modeled by homotopy. So this gives me more grading inside a homotopy group. I can choose any ROG graded representation I want. I can choose any G representation, I'll get a corresponding homotopy group. And all of these homotopy groups form this pi big star of G, which is the ROG graded homotopy group of G. So it has more grading in it. In fact, so we have the Mackey functor, and we have this extra grading. We have the representation spheres, the ROG graded homotopy groups. We can actually do both at the same time to get the Mackey functor valued ROG graded homotopy group of X. And this has a lot of structure, which is very useful for computations, which I'll explain later on. So this is contains a lot of data. Okay, so now I'd like to recall some classical theories. So classically, we have the Brown-Peterson spectrum, and associated with it, there's a tower, which is obtained by quotienting out the generators of pi star of BP. So at each stage of the tower, we have the BP ends, BP bracket ends. These are called the truncated Brown-Peterson spectra, and their homotopy groups is a polynomial ring which contains only the first n generator of the pi star of BP. So BP0, at the very bottom of this tower is HC, the Eilenberg-MacLean spectrum. So BP1 is connective K theory, connective K, little ku. And what you can do is that if you take this BPN, you take this Vn, and you can invert it. And after inverting Vn, this gives you a theory called En, which is the Johnson-Wilson theory. Okay, so this is what happens classically. Associated to BP, you have a tower, and you can create cohomology theories from it. Okay, so the whole story can be lifted C2 equivariantly if we replace BP by BPR. So C2 equivariantly, there's an analogous tower you can make by quotienting out equivariant generators of BPR. So at each stage, you have BPRN, and the underlying homotopy group of BPRN is the same as the homotopy group of BPN. It's a polynomial ring with the first n of the first Vn's. BPR0, if I look at the bottom piece of this tower, is the Eilenberg-MacLean object associated to the constant Mackey functor HC. And this is proven by Hu and Krish. And if I look at the second stage, BPR1, that is the connective Atiyah's real K theory, little kr. Now, so if I take each of the Vn's classically, each of the Vn's lies in pi 2 times 2n minus 1 of BP. C2 equivariantly, the lift to become generators in the equivariant homotopy group BPR. So this 2 here is replaced by a rho. So, and the Vn is lifted to Vn bar, which is an element in the C2 equivariant homotopy group BPR. And what you can do is that you can take BPRn and you can invert Vn bar. And what you get is a C2 equivariant spectrum called the real Johnson-Wilson theory. So the real Johnson-Wilson theory was this construction was first constructed by Hu and Krish, and Hu and Krish also subsequently studied it, and it has also been studied extensively by Critchlow, Wilson, and Lorman. And even more recently, there have been more studies on ERN by JD, Gutruan, and Vitaly Lorman. So this is the real Johnson-Wilson theory, which is the C2 analog for the Johnson-Wilson theory. Okay, so I talked about the non-equivariant case and the C2 equivariant case. You might ask, well, what happens at higher groups? So at higher groups, there's a functor, the Hill-Hopkins-Ravenel norm functor, which takes its input a C2 equivariant spectrum, and the output is a G equivariant spectrum. So C2 is a subgroup of G, and for the purpose of this talk, my group G is always going to be a cyclic group of order 2 to the m. So the Hill-Hopkins-Ravenel norm functor takes in a C2 equivariant spectrum and spits out a G equivariant spectrum. So I can apply this construction to MUR, and the theory I get is MUG, which is the norm from C2 to C2m of MUR. So just as an example, if G is C8, then MUC8, the underlying spectrum, is smash product of 4 copies of MU. And very roughly speaking, if I imagine MU as a space, then the C8 action is sending the point A, B, C, D, is sending A to here, B to here, C to here, and is sending D all the way to the front and applied by this C2 action. So very roughly saying, that's what the norm functor is doing. All right, so if you take pi star of MUG, and if you look at its underlying homotopy groups, that has a G action on it. And this underlying homotopy group, equipped with its G action, carries a universal property. So in particular, more specifically, it carries the universal G equivariant formal group law such that the C2 action corresponds to the -1 series. So there's a universal property that's carried by the underlying homotopy groups. Now that's the construction for MUR. I can do the same construction for BPR as well. I can define the norm, BPG, to be the norm from C2 to C2M of BPR. And if I too localize, then MUG splits as a wedge of suspension of BPG. So these are the higher group analog for BPR and MUR. All right, so G equivariantly, we have these theories MUG. You might ask, well, what are these theories good for? Well, they're good for a variety of things. So one thing they're good for is that Hill, Hopkins, and Ravenel used it to solve the Kervaire invariant problem, which is a long-standing open problem in algebraic topology. So in 2009, Hill, Hopkins, and Ravenel proved that the Kervaire invariant elements theta j do not exist for j greater or equal to 7. And here's the outline of what they did. So they started with MUC8, and which is a C8 equivariant spectrum, and they inverted a certain class in the C8 equivariant homotopy group of MUC8. So this grading D actually lies in 19 row 8, pi 19 row 8 of MUC8. So where row 8 is the regular C8 representation. So they get the spectrum, which is a C8 equivariant spectrum, and they define omega to be a C8 fixed point spectrum. And they subsequently proved 3 theorems associated with omega. So the first theorem is called the detection theorem, and it says that if theta j exists in the homotopy group of the sphere, then its Hurewicz image in omega is not 0. The second theorem is the periodicity theorem, which says that the spectrum omega is 256 periodic. And the third theorem they prove is a gap theorem, which says that there's a gap in its homotopy group. So in particular, pi I of omega is equal to 0 for I equal to -1, -2, and -3. And these three theorems pieced together will give you the Kervaire invariant theorem. So I want to give you like a baby version of omega to give you an idea of how you can see these theorems from a spectral sequence. So this is a spectral sequence about a baby version of omega. You're going to see it again later in the talk. But what the periodicity theorem is saying is that this element here this class here is a permanent cycle. It doesn't support any differentials. And the gap theorem is that there's a gap. And the detection theorem says that the Kervaire invariant elements are detected at the E-infinity page. Okay, so this is a baby version of the HHR detecting spectrum. This baby omega is 32 periodic, and that's the periodicity generator. But the actual detecting spectrum is 256 periodic. Okay. All right. So now we have all these MUGs and BPGs. We can create analogous tower as we did non-equivariantly and C2 equivariant. So using the techniques of HHR, you can create a G equivariant tower, which starts with BPG, and you start quotienting it out by its generators into equivariant homotopy groups, and you can create a tower like this. At each stage of the tower, the homotopy group for each of these BPNs is a polynomial ring with a bunch of generators. So by this notation, I mean that this G times Ri is a bunch of generators, and the G adjunct, so if gamma is the generator for G, is sending this generator to the next one, this one to the next one, and all the way to the last one, and sending the last one to the one in the beginning with the minus sign, with a minus to the degree of Ri. So this is a description of the underlying homotopy group together with how G is acting on it. Okay. So now if I look at the bottom piece of the tower, BPG0, this is the Eilenberg-MacLean object associated with the constant Mackey functor Z. And this is the Hill-Hopkins-Ravenel's reduction theorem. It's a technical theorem in the Kervaire invariant paper where they prove the very bottom piece of this tower is HC bar. Now, what's the point of this tower? Is that, okay, what I said before in the last slide is that we know that MUC8 detects the Kervaire invariant element. But what's true is that even if you just look at BPC8-1, the very first stage of this tower, that spectrum, the CA6 point also detects the covariant element. So if you want to do computations to see what's going on, you don't have to do the full computation with MUCA. You can just focus your attention with this truncated VPG, which is much smaller. And which means, so what I mean is that we see less class on the E1 page of the slice spectral sequence, and it's easier to compute. Okay. So even the first stage of the tower for BPCA will detect theta J. Okay, so now we have these theories. We call these theories the HHR theories. How do we analyze these homotopy groups? So we analyze these homotopy groups by the slice spectral sequence. So the slice spectral, I would like to quickly say a few words about the slice spectral sequence, the equivariant slice spectral sequence. They are an analog of the non-equivariant Postnikov tower. So here's a quick definition. So if G is a finite group, then I'm going to let rho H to be the regular representation of H, where H is a subgroup of G. I'm going to define the slice cells to be these spheres. I'm going to take Sn rho H and Sn rho H minus 1. I'm going to induce it up to G. So the dimension of these slice cells are going to be the underlying dimension of each of these representation spheres. And given these spheres, I'm going to define S greater than N to be the smallest full subcategory of G spectra that contains all the slice cells of dimension greater than N. And if I close it up under taking cofibers, extensions, and wedges. So non-equivariantly, this is saying I'm taking all the spheres with dimension greater than N, and I close it up under cofibers, extension, and wedges. Non-equivariantly, I have these equivariant spheres, and I'm doing the same construction. Okay. Now, I just want to remark that this is closed under taking cofibers, extension, and wedges, but it's not closed under taking fibers. Okay. So this is what S greater than N is. And I can also define S smaller or equal to N to be the orthogonal orthogonal category. So it's defined as the spectrum X such that maps from a spectrum in S greater than N to X is contractible. So given these two definitions, I can start with X and apply the Dror-Farger nullification functor, which is a special case of Bell field localization, to construct for me a cofiber or fiber sequence where it's X where I separate out. So it's a fiber sequence from Pn plus 1 of X to X to Pn of X, where Pn plus 1 of X is in S greater than N, and Pn of X is in S smaller or equal to N. Okay. All right. So now, given this, I can form a tower, and that tower is called a slice tower. So it's obtained by piecing together these P upper ends of X. So this is the tower where X sits as the inverse limit, and the co-limit is contractible. And the fibers of these towers are called the slice section. So this is the slice tower. And given the slice tower, what I can do is I can apply pi star of G, and I get a tower of homotopy groups, and that gives me a spectral sequence. So it's a spectral sequence where the E1 page is pi star G of the fibers, the slice sections, and it converges to the equivariant homotopy group of X. And the differentials we grade it in the same way as the usual Adams differential. So the dr differential goes 1 to the left and r up. So this is the slice spectral sequence which we can obtain from the slice tower. Okay, well, recall what I said in the beginning, that we're in equivariant homotopy theory. There are more structures to its homotopy group. So not only I can take pi little star of G, what I can also do is I can take pi big star of G. So that has more data. So if given the slice tower, I can take pi big star of G everywhere. And that gives me an ROG graded slice spectral sequence, where the E1 page is the ROG graded homotopy group of each of the slice sections, and it converges to the ROG graded homotopy group of X. And another thing you can do is say, hey, wait a minute, the homotopy group, they come as Mackey functors as well. So what I can do is I can apply the Mackey functor pi underlying star. And from this, I get a slice spectral sequence where each piece, each class is now a Mackey functor. And this converges to the Mackey functor homotopy group of X. So this is a spectral sequence. This last spectral sequence I said is a spectral sequence of Mackey functors. But we can also view it as a Mackey functor of spectral sequences. And both of these ways are very useful for computations later on. So what I mean by a Mackey functor of a spectral sequence, so here's the slice tower. So what I can do is I can take the C4 pi little star of C4, the C4 equivariant homotopy group everywhere. And what I can also do is I can treat X as a C2 equivariant spectrum and take pi little star of C2 everywhere. So this gives me two towers, and there are restriction and transfer maps everywhere. So, and this gives me a map of spectral sequences from the C4 slice spectral sequence, between the C4 slice spectral sequence of X and the C2 slice spectral sequence of X. So this is I can view as a spectral sequence, a Mackey functor of spectral sequences, where the restriction and transfer maps are now maps of spectral sequences. And now also, if you're feeling really ambitious, what you can do is that you can take the slice tower and apply pi underline big star. And what you get is an ROG graded slice spectral sequence of Mackey functors. And this spectral sequence has a lot of structure. It's very rich in structure. And when we're doing computations, we're using many of the structures that are within this spectral sequence. Okay, so I want to give you an idea of an example of the computation of the slice spectral sequence for a TS real K theory KR. So this picture is a picture about the Mackey functor spectral sequence for KR, where each piece here, originally they're just abelian groups, but now each symbol is a Mackey functor. Now, so the C2 slice spectral sequence of KR was first computed by Dan Duggar. So Duggar, in his thesis, he computed the C2 slice spectral sequence of KR. What he found is that the odd slice sections of KR is 0, and the even slice sections are all regular suspensions of HC bar. And what's good about that is that you can compute this E1 page completely. So when you compute this E1 page, you're computing the pi big star of SN row smash HC. And this is the Verdun homology of the representation sphere SN row with coefficient in the constant Mackey functor. Or you can view it as the homology of a point, the Equivariant homotopy group of HC bar. And this can be fully computed. So I'm just going to say inside here, this has been fully computed. There are certain classes called A sigma and U2 sigma. That's the Euler class, and that's the orientation class. And here's the picture of the ROG graded homotopy group of HC bar. So I want to apologize to the motivic homotopy theory people. The grading I use is slightly, it's a naive grading. I know the motivic homotopy theory people, they like to use the total grading and the twist, but this picture is led like a shift, like a twisted, like a rotation of what motivic homotopy theory like to write. But the point is, all of the homotopy group has been computed. And from this, we can write down the E2 page of the slice spectral sequence. So the E2 page is all the symbols you see here without the differentials. And it turns out there are D3 differentials which can be computed. Now, I just want to, so we talked, this is the Mackey functor. This is a spectral sequence of Mackey functors, but it's also, I can also view it as a Mackey functor of spectral sequences. So when I view it as a Mackey functor of spectral sequences, this spectral sequence consists of two spectral sequences. One is about the spectral sequence computing the underlying homotopy group of KR, which is pi star of KU. So you see a Z in every even degree, and there are no differentials. The second spectral sequence you see is a C2 equivariant spectral sequence computing the C2 equivariant homotopy group of KR, which is KO. And this is the slice spectral sequence computing pi star of KO. And you can read the Z2, Z2, 0, Z, 0, 0, 0, Z pattern here. And their names that's coming from the homology of a point. So when you look at the spectral sequence in the ROG grading, there are two periodicities. One periodicity is given by B1 bar, and that gives you a row periodicity. And another periodicity is given by this orientation class, and this gives you a 4 minus 4 sigma periodicity. So the upshot is that these two periodicities together, you can do some linear combination of these, and they give you a row periodicity and an 8 periodicity. So if I multiply this row by 4 and add it to 4 minus 4 sigma, I get an 8 periodicity. So the upshot is that in the C2, when I look at the ROG grading, there are more periodicities, and this row periodicity corresponds to the complex spot periodicity, and this one corresponds to the real spot periodicity. And both periodicities are encoded in the ROG graded spectral sequence. And these two periodicities correspond to two equivalents. So when we're computing the slice spectral sequence of the truncated Brown-Peterson, the truncated BPGs, the off slices are also 0, and the even slices are wedges of suspensions of HC by these regular slice cells. So the point is that the E1 page is also computable. Okay, so this is how we're going to compute the slice spectral sequence for these BPGNs. And you might ask, well, what about the detection theorems, the gap theorems, and the periodicity theorems? What do we know of these theorems for these generalized HHR theories? So I want to look at the C2 case first. So C2 equivariantly, I have a tower associated with BPR, and I can take the C2 fixed points everywhere. And I can ask, well, what is the Hurewicz image for each of these pieces? So a couple of years ago, Guchuan Li, myself, Guojun Wang, and Zhou Xu proved that there are families on the E2 page of the atom spectral sequence that are detected by the Hurewicz map from pi star of the sphere to pi star of the fixed point of BPR. So we proved that the Hoff, Kervaire, and the kappa bar families are detected by the Hurewicz map. And furthermore,
Danny, what do you mean by kappa bar families?
I'm going to define in the next slide.
Okay.
So the families on the E2 page of the atom spectral sequence.
Okay,
they're the G. Yeah.
I can wait.
Yeah. So from that, what you can also deduce is that the C2, if I take the C2 fixed point for each of these truncated theories, that detects the first n elements of the Hoff and Kervaire family and the first n-1 elements of the kappa bar family. So BPR detects all the elements, and BPR only detects the first n elements. But as this n grows, it'll start to detect more and more elements. Okay, then I ask, well, what are these families defined? So the Hoff family is defined on their families on the E2 page of the atom spectral sequence. And the Hoff elements they're represented by the HI. So they're on the one line of the atom spectral sequence. And by atom solution to the Hoff invariant 1 problem, we know that HI survives and detects the Hoff map for I equal to 0, 1, 2, 3. But when I is greater or equal to 4, all of these HIs support a differential and they do not survive the atom spectral sequence. And the next family was the Kervaire family. That's the HJ squared. It's a family on the 2 line on the E2 page of the atom spectral sequence. We know that HJ squared survives the atom spectral sequence and detects theta J for J lesser equal to 5. So that's hard computations done by Jones, Mahol, Tangora, and people. They did hard computations with the atom spectral sequence. Barry, Jones, Tangora, and Mahol. And the Kervaire problem shows you that HJ squared support a differential in the atom spectral sequence for J greater or equal to 7. And so they do not survive to become the theta J's. And the fate of HJ squared is unknown. So that's the Kervaire family. The next family is the kappa bar family. And this family called the GKs on the 4 line on the E2 page of the atom spectral sequence. So the first 2 elements survived. G1 survived to become kappa bar, hence the name to kappa bar family. G22 survived to become this element called kappa bar 2. And I think the name of kappa bar 2 is actually due to Dan Isaacson. Jolie told me that Dan first called this element kappa bar 2. So then we decided to call this family the kappa bar family.
I think that's right, yeah.
Yeah. And the next element, G3, is the STEM 92, and it supports a non-zero differential. So I think it supports a D5. That's what Jolie told me. And so it does not survive the atom spectral sequence. And the fate for the later GKs, they're still unknown. But the detection theorem tells you that if they survive the atom spectral sequence, then they must all be detected in the Hurewicz image to the C2 fixed point of BPR. Okay, so this is a picture of the slice spectral sequence showing you that these elements are detected. So that's the Kervaire and the Hopf and Kervaire, eta is a nu squared kappa bar, and then C sigma squared and kappa bar 2. Okay, so that's one use for the HHR, these HHR spectra, they detect the Kervaire invariant elements. So it turns out that these HHR spectra has a connection to chromatic homotopy theory as well. So in chromatic homotopy theory, a central object to study is the Morava E theories En, with the stabilizer group action from the Morava stabilizer group. So inside this Morava stabilizer group, Sn, there's a central C2 subgroup. And the C2 subgroup acts on En star, which is the universal deformation ring, as the -1 series. And since En is complex oriented, there's the formal group law over En star is classified by a map from Mu star, the Lazard ring. And there's a C2 action on Mu star, and there's a C2 action on En star. And this map of rings is C2 equivariant. Now, what we know is that on the level of spectra, there are C2 equivariant spectra that lift this action on each side. So there's MUR with this C2 action coming from complex conjugation, and there's also En as a spectrum, and C2 by the Gortz-Hopkins-Miller theorem, there's a C2 action acting on En by E infinity ring maps. Now, I just want to remark that even though these two C2 actions on the level of algebra they're compatible, but it's unclear whether on the level of spectra they're compatible, because the C2 action on MUR is coming from geometry, it's coming from complex conjugation, whereas the C2 action here is coming from the Gortz-Hopkins-Miller obstruction theory. It's constructed purely using obstruction theory. And the natural question to ask is that can we lift this algebraic C2 equivariant algebraic map to become a C2 equivariant map, C2 equivariant spectrum? So can we lift it? So the answer is yes. So Jeremy Hallen and I proved that the Morava E theory is real oriented. So we received a C2 equivariant map from MUR to En. There's a C2 equivariant map from MUR to En. And I just want to remark this is a C2 equivariant map on the point set level. This is not, it's obvious that there's a C2 equivariant map in the homotopy level, but this is a C2 equivariant map on the point set level, and it induces a map of C2 homotopy fixed point spectral sequences. And from that induced map on the C2 equivariant homotopy fixed point spectral sequences, we can compute ENHC2 at all heights. So Jeremy and I used this real orientation and analyzed this induced map on the homotopy fixed point spectral sequence, and we computed ENHC2 at all heights. This is an example showing you the computation for E3HC2. So this is the homotopy fixed point spectral sequence for E3HC2. The differentials happens in stages. The first differential are the D3 differentials, then you have the D7 differentials, and then the D15 differentials. Afterwards, the spectral sequence collapses, and you're at the E infinity page. And you might see that I have also marked the classes here by elements in the stable homotopy group of spheres. And that's because there exist forms of E theory that factors through each stage of the tower associated with BPR. So there exists a C2 equivariant tower. So non-equivariantly, we know there exists E theory that factor through each of the BPNs. This is also true C2 equivariantly by using the real orientation. And what I can do is after I take its fixed points, I get then from the detection theorems for BPRN, which we already know, then we can deduce the detection theorems for the homotopy fixed point for the ENs. And from this, we get that if I look at ENHC2, it detects the first n elements of the Hopf and Kervaire family and the first n-1 elements of the kappa bar family. And in fact, the Fourier images of the ENHC2 and BPRNC2, they are the same. Okay. I'm just going to skip this remark because Hannah told me this talk is only 50 minutes, so I'm just going to skip it. So now we have the detection. Now we know some detection theorems. You might want to ask, well, what about the periodicity and the gap theorems? So we know the periodicity and gap theorems for all these HHR theorems. And we know the real orientation gives us a link between the HHR theories and E theories. What can we say about the periodicity and gap for the Morava E theories with a fixed point action? So what we know from the computation is that pi star d in HC2 is 2 to the n plus 2 periodic, and there's also a gap. And the question to ask is what happens at bigger groups? So this is what I explained what happens to equivariantly. What about bigger groups? So what you can do is that you can use the Hill-Hopkins-Ravenel norm functor to convert the real orientation into a G orientation. So the theorem says is that if G is a finite subgroup of the Morava stabilizer group that contains this central C2, then there is a G equivariant map from MUG to EN. So this becomes the real orientation. When I apply the norm, it becomes a G equivariant orientation. And it turns out a similar tower will exist G equivariantly as well. So G equivariantly, there exists this generalized Brown-Peterson tower. And so this is a joint project with Ines and Minkong. We showed that there exist good forms of E theory with a G action that factors through each of these quotients. So we used formulas obtained from BPC2M, and we constructed E theories so that they emit factorizations, just like they do classically. Okay, so now if I take each piece of that factorization, I can start to, this is what a piece looks like. I can start to leverage the techniques developed by Hill-Hopkins-Ravenel to show that pi star of the homotopy fixed point of E with this finite G action is periodic with this period, and there's also a gap. So this is joint work in progress with Ines Baudry, Mike Hill, Guojun Wang, Zhouli Xu, and Minkong Zeng. So we're in the process of using this factorization and leveraging the techniques developed by HHR to prove periodicity theorems and gap theorems for Morava E theories. Okay, so with the time I have left, we can finally get to some computations. So the first computation I want to talk about is this tower, the first piece of this C4 equivariant tower. The first piece is BPC41, and there exists E2 with a C4 action, so this factors through BPC41. The more precise relationship is that if I take BPC41, I invert the generator, and I apply the K2 localization, then the C4 fixed point of that is E2HC4. So here, D is the element in the ROG graded homotopy group of BPC41. And this is a picture of the slice spectral sequence of BPC41. And this is computed by Hill, Hopkins, and Ravenel. An analog of this spectral sequence using the homotopy fixed point spectral sequence has also been computed by Mark Behrens and Kyle Wormsby. And so this spectrum is related to TMF05. And this is the infinity page of the slice spectral sequence. And just like the case for KR, if I look at the ROG graded homotopy groups, if I look at BPC41 and I invert this D, it has 3 ROG graded periodicities. One of them is a rho 4 periodicity. One of them is a 4 minus 4 sigma periodicity. And another one is 8 plus 8 sigma minus 8 gamma lambda periodicity. And 1 sigma and lambda degenerate the real representation ring of C4. So together, I can do some linear algebra. And what I get is I get a 32 periodicity for D inverted BPC41. So the computation is a 32 periodic computation. So here are some Hurwitz images that's detected by BPC41. So I just want to make a remark is that when you look at the Hurwitz images that's detected by BPR, the C2 fixed point of BPR and the C4 fixed point of BPC4, there's a drop of filtrations. Is that for the Hopf elements and the Kervaire elements, as you move up the group, the filtration they're being detected moves down. So I just want to, basically what I mean is that there's the intuition is that as the filtration drops down, then the elements are being detected more and more accurately. And in fact, there's a detection tower. This detection tower is due to Mike Hill. which starts with the C2 fixed point of MUR, and the next level is the C4 fixed point of MUC4, and the C8 fixed point of MUC8. And the idea is that as you move up the tower, more and more elements in the stable homotopy group of the spheres are going to be detected. And furthermore, by the real orientation theorem, we know there are maps from each of the fixed point of the MUGs to the homotopy fixed point of the E series. So analyzing the Horowitz image of this tower will give us the Horowitz image for each of the fixed point for the ENs with the finite group action. So here's an open question proposed by Mackey. It's wide open. So, and the question asks, what is the Horowitz image of this tower? So what are all the elements in the homotopy group of spheres that can be detected by this tower? And by the real orientation, essentially what this question is asking is that if you look at all the ENs and with the finite two group action, then what is the Horowitz image that's detected by their homotopy fixed point? Okay, so what are some techniques for computing the slice differentials? So I'm just going to take MUC4 as an example because all of our computations, what I'm going to show you, they're all C4 equivariant. There are restriction and transfer maps between the homotopy groups. And there's also a norm map that's coming from the fact that MUC4 is a commutative C4 spectrum. And this induces map of spectral sequences. So associated with MUC4, there's a C4 slice spectral sequence and a C2 slice spectral sequence. And the restriction and transfer map are maps of spectral sequences. The norm map is not quite a map of spectral sequences, but it stretches out differentials under suitable conditions. So here's a theorem due to HHR that tells you how to stretch out differentials. So roughly what the theorem is saying is that suppose you start with a DR differential in the C2 slice spectral sequence. Then if certain desirable conditions are satisfied, then you can apply the norm to obtain a D2R minus 1 differential in the C4 slice spectral sequence. So I remember the first eCHT talk I went to was by Mackey, and this is what Mackey talked about. He was explaining the structures inside the spectral sequences and how it can leverage the norm to produce this theorem, to stretch out the differentials. Okay, here are some formulas telling you how restriction, transfer, and the norm work, but don't worry about them. I'm going to show you a picture because picture is worth 1,000 words. So the picture is that here's a C2 slice spectral sequence, and here's a D7 differential. Just from that one D7 differential, I can apply the restriction, transfer, and the norm to give me 3 different kinds of differentials in the C4 spectral sequence. So by applying the restriction, I get a D5 differential. By applying the transfer, I get a D7 differential. And by applying the norm, I get a D13 differential. So just by using the structure of this very rich structure in the Kervaire homotopy theory, this ROG gradient and this Mackey functor structure, just from one differential in the C2 spectral sequence, I get 3 differentials in the C4 spectral sequence. And this this is how it really helps the computation a lot. Okay, so with a couple minutes I have left, let's go back to this picture, which I showed at the beginning. What is this picture? This is the slice spectral sequence for BPC42. So this is the next stage of the tower for BPC4. It has a map to E4 with the C4 action. And the precise relationship is that if I take BPC42, I invert an element and I K4 localize, then the C4 fixed point is equal to the E4 HC12. So here, D2 again is an element in the ROG graded homotopy group of BPC42. And this is joint work with Mackey, Guojun Wang, and Zhou Xu, where we computed completely the slice spectral sequence for BPC42. We computed all the differentials in the slice spectral sequence. So here's the picture of these differentials. The lower differentials I didn't draw, but it starts at the E13 page. We've got D13, D15, D19, D21, D23, 27, 29. All of these ones are obtained by the norm: 31, 35, 43, 51, 53, 55, 59, 61. All of these are obtained by the norm, and then after which the spectral sequence collapses, and we get the E-infinity page. We also know some heroic images. Oops, I didn't draw them here, my bad. But we do know some heroic images that are detected by BPC42. And we're in the process of finding more heroic images. Oh, I drew them here. So we do know some heroic images. But I think I'm running slightly out of time, so I'm just gonna skip this part. So just like BPC41, there are 3 periodicities in the ROC4 grading. And if I piece them together, I get an integer periodicity. So this spectral sequence is a 384 periodic spectral sequence once I invert a generator. Okay, so that's the first spectral sequence. What about the second spectral sequence? This second spectral sequence looks similar, and this is the C4 slice spectral sequence for BPC81. So this is the BPC81 lies in the first piece of the BPC8 tower, and the C8 fixed point of this spectrum detects the Kervaire invariant, all the Kervaire invariant elements. So the precise relationship is that if I take BPC81, I invert a generator D inside its C8 homotopy group, and I K4 localize, then the C8 fixed point is E4HC8. So at height 4, it turns out at prime 2, C8 is the maximal finite 2 group inside S4. So in some sense, this E4HC8 is the height 4 analog for the TMF, because TMF at the prime 2 is essentially E2HQ8, because Q8 is the maximal finite 2 group inside S2. So this is joint work with Chatham, Hannah Jia Kong, Guozhen Wang, Zhou Xu, and Mingkong Zhang, where we computed the C4 slice spectral sequence of BPC81. So here's a picture. Again, it starts at the E13 page. We got a 13, 15, 19, 21, 23, 27, 29 differentials. And you might start to see that things look a little similar to the case for BPC42. All the length of the differentials, whenever there's a dr differential in BPC42, there will also be some dr differentials in the C4 slice spectral sequence for BPC81. And it turns out that the 2 spectrums are related as follows. If I restrict my attention to C4, then BPC42 has this map to BPC4. But BPC4 also has a map to the, if I look at BPC8 and restrict my attention to it as C4 spectrum. So the 2 spectral sequences are related. And in fact, I can start with the differentials here and do some zigzag arguments to get the differentials here. And our computations show that as a C4 spectrum, the C4 fixed points of BPC81 with D inverted is 128 periodic. But the advantage, one advantage I would like to promote for BPC81 is that this BPC81 has a C8 action. This BPC82 is also about the spectral sequence of a height 4 theory, but BPC42 only has a C4 action. It doesn't have a C8 action. Whereas BPC81 is encoding E4 with its C8 action, with its full C8 action. And it's a current project to compute the C8 slice spectral sequence of BPC81 completely. By HHR's periodicity theorem, we know it is 256 periodic after inverting D. And once we have computed the slice spectral sequence completely, that will give us information about E4HC8. And the question to, interesting question to ask is that what are the heroic images of the C8 fixed point of BPC81? We know the Kervaire, all the Kervaire elements are detected, but are there any other interesting elements in the homotopy group spheres that are detected by this C8 fixed point? Okay, that's all I want to say today. But you know, this is some computations, and hopefully in a couple of years, couple of months, if someone asks you, well, what happened in Danny's talk? It would be good if you might want to say, oh, I don't remember anything, but I guess Danny has some good pictures. So all of these pictures I want to advertise these pictures. All of these pictures are drawn using Hodge-Chatham's spectral sequence package and a program. So what Hood did, so Hood is a grad student at MIT. He's a student of Haynes, and in fact, he's on the market this year. So what Hood did is I explained how to do the slice spectral sequence computation, and he automated part of the process for the slice spectral sequence computation. He made a program to automate part of the computation. And it's an interactive program in that I can put in a differential by hand, and the program automatically converts it into a piece of code, and then it will spit out the next page immediately. And each of the dots, there's a web version. If I hover over each of the dots, it will show me the names in the slice spectral sequence for the dots. So I just want to give a big shout out for Hood. All of these pictures are made possible by his program, and he has worked very hard to produce these pictures. Okay, that's all I want to say. Thanks.
Okay, I'm going to unmute everyone so we can thank Danny. Okay. And then I will mute everyone again to cut back on the background noise. Okay, and are there any questions for Danny?
Oh, this is Doug.
Hey, Doug.
Hi, Danny. A few slides ago, you said D was in the dimension of D was 25, row 8. Where did that come from?
So the dimension of D in the HHR one is in 19, row 8.
Yeah.
So in order to make this K4 localization process work, we have to invert an extra generator so that when we K4 localize, we get the coefficient ring for E theory.
An extra generator of something dimension 6, row 8?
In dimension 6, row 8, that's right.
What is that?
So that generator is, you look at the formula of V3. So there's a map from BP to BPC8, pi star BP to pi star underline of BPC8. You look at the image for the V3, and you analyze this image, and that the 6, row 8 comes from a piece of that that formula.
Okay.
Yeah, it's a similar situation. I want to remark the similar situation happens at BPC42. So if you want to induce a periodicity for BPC42, for HHR, you inverted certain generators. But in order to get the coefficient ring for E theory after K4 localization, you have to further invert another generator in degree 6, row 4. So here is 6, row 8, in there is also 6, row 4. And it's also coming from the formula of where V3 maps to.
Okay, thank you.
Yeah.
Other questions? I had a question about, I think it was like a question, you said it was a question of Mike Hill about the limit of the sort of detecting tower or something.
Yeah.
Isn't there, I seem to recall something about eta cubed or 4 nu.
That's right. So Mike Hill proved that eta cubed is not detected anywhere in this detection tower.
And is there any sense of like what property is that eta cubed has that means, I mean, it's the first element in some family or something that isn't detected? Is there any kind of sense of what that it might be?
I don't know, but for my impression of it is that, so for the Morava stabilizer group, for the finite 2 groups, when the height is not divisible by when the height is divisible by 4, it's always cyclic. But if the height is 2 mod 4, then you get a Q8 as the maximum 2. So eta cubed is detected in E2 HQ8. Okay. So for eta cubed is detected in TMF. What Mike Hill's theorem says is that if you look at all these cyclic group fixed points, eta cubed is not detected anywhere. So,
okay. All right, great.
Yeah.
Okay, other questions? Okay, if not, I'm going to unmute everyone again, and we can thank him one last time. Okay. Thanks, everyone.